Okay, so now I'm moving on to number 5 from the 2023 AP exam FRQ questions. So this one is looking like obviously an evolution type of question, and we've got some evolution trees here. So this one says, ruminants are hoofed animals, including cattle and sheep, that have a unique 4-chambered stomach specialized to digest fiber-filled grass. Researchers studying ruminants are investigating the morphological and molecular characteristics of different ruminant families in order to determine the evolutionary relationship among the families. Cladograms of several ruminant families are constructed based on morphological data, which is figure 1A, and molecular data, which is figure 1B. Table 1 shows a sample of the morphological characteristics present in each family used to construct the cladogram in figure 1A. Okay, so let's look at this figure now. It says cladogram of 6 ruminant families based on A, morphological data, and B, molecular data. So this is really, really important. The fact that A is based off of morphological data. So I'm just gonna write that here so I don't forget. And then this is molecular data. And then they give you a table here, which is morphological characteristics found in each ruminant family. So you have extra tooth material, third stomach, double opening for tear ducts, and then it tells you which ones do and don't have them. Okay, the X is going to indicate that they do have them. Alrighty, so let's just dive in for the first question and see what it says. A says, describe how a scientist would use a comparison of the DNA sequences of different organisms to suggest the most likely evolutionary relationship among the organisms. Okay, so for this one, they're asking you how you use DNA to determine evolutionary relationships. So that one is fairly straightforward. What you're going to do is you have the DNA sequences. DNA sequences that are more similar to each other are going to represent animals that are more closely related, right? So we share, 99% of our DNA with monkeys, right? Because we're evolutionarily closely related. We don't share as much DNA, with fish, for example, because in terms of evolutionary time, we're a lot less related. So all you have to say for this one is going to be that the more similar the DNA sequences are, the more closely they're related. Okay, so for this one, DNA sequences that are very similar indicate closely related organisms. Okay, so that's all you had to say for this one. Okay, so part B says, based on figure 1, explain why Bovidae is likely to be more closely related to Moschidae than it is to Giraffidae. Okay, so for figure 1, which is our cladograms, I'm just going to highlight where those are. So Bovidae, got it here, and then our Moschidae here and here, and then Giraffidae is here and here. Okay, so we can see in A that Giraffidae is more closely related to Bovidae, right? However, in B, Bovidae is more closely related to Moschidae. Okay, so we're seeing 2 different patterns here. They're now asking you, why is it more likely that the Bovidae is more closely related to Moschidae than it is to Giraffidae? Okay, so they're asking why this is more likely, right? Because this one is showing you that Bovidae and Moschidae are more closely related. This is showing you the opposite. So they're asking you, why would this one be correct? And the answer for that one goes to the fact that we have here. B is molecular data and A is morphological data. And for our cladograms and for determining evolutionary patterns, we remember learning about, homologous and analogous structures and how you shouldn't use morphological data to determine, evolutionary relationships, right? Because for convergent and divergent evolution, you have two organisms that are not closely related but resemble each other, right? They may morphologically look similar, like our sugar glider and our flying squirrel example, right? They are not evolutionarily closely related, even though they look very similar. That's convergent evolution. So that is why you can't go off morphological data, right? They are not closely related. However, in our molecular data, we can see that the Bovidae and the Moschidae are more closely related. Now, we want to use molecular data. So this is going to be comparing DNA sequences, right? It is more likely that B is correct because molecular data is better at determining evolutionary relationships compared to morphological data. They might not be as reliable, again, because of things like convergent evolution. So for B, I would say, so the molecular data supports this, right? Because the molecular data said that Bovidae and Moschidae were more closely related. So molecular data supports this, and the morphological data does not. And so molecular data supports this. Molecular is more reliable. Than morphological. I think that's all you had to say for this one. Yeah, it's more reliable, or you can say that morphological isn't reliable because of, evolutionary trait relatedness, right? Again, those convergent structures. You should always, always, always use molecular data. You cannot use morphological data because, again, convergent evolution, you can't just look at an animal and determine if it's related. The best way to do that is by comparing DNA sequences. Okay, so B is much better than A, and B is much more accurate and reliable than A is. Okay, C says, using the template in the space provided for your response, represent the points at which characteristic 1 listed on table 1 evolved by marking X on the line of the cladogram in the correct locations. Okay. So, they're looking for when characteristic 1 evolved. So characteristic 1 in our table is extra tooth material. So we're not looking at any of the other characteristics. We're looking at these ones. Oops. They want to know where this developed. So the only two that have extra tooth material is Bovidae and Antilocapridae. So since this table is our morphological characteristics, we're going to use A, which is our morphological data. Okay, so we have to model it on A. Don't model it on B because this is not molecular data. We're doing it morphologically, so we're using A. Again, the only two that have it are Bovidae and Antilocapridae. So where are those? We've got Bovidae here, and then this one here. Okay. So my first X is going to be right here, okay? Because Bovidae does have the extra tooth material, but Giraffidae doesn't, right? You don't have an X here. Therefore, I can't put it here because that would mean that both should have it. So it has to be specific just to Bovidae, therefore it has to be right before it. However, you have this Antilocapridae, which also has extra tooth material. So for this one, the X, you actually have to draw 2 in this case. Right here is what developed, right? Because this is also the only one affected. Now, despite the fact that both of these do have extra tooth material, I cannot put the X here because that would mean that Giraffidae, Moschidae, and Cervidae would also have extra tooth material. And then based on our table, we know that's not true. So these actually developed separately, which is interesting. So you actually had to draw 2 of these. And so there were 2 separate evolutionary events where they had extra tooth material develop, okay? So this is, like an example of convergent evolution. So those where your 2 X's would be. You can put them anywhere else because these 4 do not have them. So you should in no way have an X that would indicate that those 4 would have extra tooth material. Okay, let me just erase my scratches so that we can see the final product. This is what yours should look like with those 2 X's right there on those branches. I wouldn't be able to put it here because that would mean Cervidae has it as well. Okay. Alrighty, so our last one is D. And D says, based on figure 1A, explain why a characteristic found only in the Cervidae and Bovidae families is more likely evidence of convergent evolution than it is of common ancestry. So I basically already answered this without knowing it. So a common characteristic of Cervidae and Bovidae. This is very, again, similar to the question previously. So Cervidae is here and Bovidae is here. They are saying that if both of these have a characteristic found only in these ones, okay? So I'm just gonna erase these X's just so it doesn't get confusing. They are saying that both of these are the only ones that have the trait. Why would this be convergent evolution? The reason it's convergent evolution is because they're not closely related. There was not one evolutionary event that caused both of them to have it. There were 2 separate evolutionary events, right? If there was one evolutionary event, it would have to be right here, and that would mean that these 3 would also have the trait. However, since only these 2 have the trait and they're not closely related, again, it had to develop here and then it had to develop here on 2 separate occasions. So this is, again, an example of convergent evolution where you have 2 not closely related organisms that develop similar traits through 2 separate evolutionary events, okay? They did not both develop these because they're closely related. They developed them separately. So if I wanted to put that into words for our answer, you can say they arose independently in Cervidae and Bovidae because the common ancestors don't have them, okay? So let's write that down. BC, I think this one should be D. Yeah. So they are D because the characteristic separately. I would say that they both have the trait, but Giraffidae, Moschidae, and Antilocapridae do not. I'm just going to put the acronyms. We'll put G, B, and A. Okay, so that should be fine for this question. My pen's dying, so it's a little bit messy. So it's more likely that these characteristics arose independently because the common ancestor wouldn't have developed this. If the common ancestor did develop this, then you would see it in Giraffidae, Moschidae, and Cervidae. Okay. So that's it for this one. I believe this one was 4 marks as well, 1 for each part. So that is question 5.